Okay, so what we have been doing recently on Zulip and in the last lecture, we were investigating equality, and we saw that we have like four. First of all, we want equality for any type to be an equivalence relation, so it has to be reflexive, transitive, and symmetric. And we also have a substitution rule, which I haven't written down properly here because it's kind of a bit complex maybe. But the idea is that we have used it, so we know how to use it. So here's how we used it. We want to justify rules like apply the same function to both sides, which we do all the time in mathematics without having it as an axiom. So how did we infer this idea? We want to start from an equation like u equals v, and we want to apply some f on both sides. So just let me ask you something to wake you up here, which was a pink homework or something like that. Supposing that this is like alpha, what are the other types involved here? So what should this, what should the quality of this, the type of this equality be? Ideas? It could be alpha, but it's kind of too restrictive. Thanks for the answer. Because f here, okay, we should, in order to answer this question, we should look at f. So I have a function application here, which we will discuss today, how it works and what we can infer about it. But the idea is that this f could be from alpha to any type beta. So the type of f is definitely from alpha. How do I know? This part I don't have any liberty here, because as an input, as an argument, I'm giving u to f, and I know that u is an alpha because I have alpha here. So this part I have no control over, but there is no reason to restrict what I will put on the right-hand side, right-hand side of this arrow. So I want to be more generic and put any type vita. And this means that now I have a better idea on what to put here. This should be a vita, because by applying f to u, this becomes something of type vita. Yes, that is a question, yeah. F? F alpha, in what sense? Like this? No, I get what you mean. I mean here, like f alpha or something like that? We're going to have a type error, because if you write something like f and here alpha, I have a type error because f wants things of type alpha, takes things of type, elements of type alpha to elements of type beta. And here, this is, what is the type of alpha? It's a type. Does that make sense? It's like, to give you a concrete example, let's say you have a function from the natural numbers to the real numbers or something like that, and you're trying to apply f to the actual set of the natural numbers. Okay, so it's a similar kind of type error. So, yeah. And the same goes here, right? This is a vita as well. So I just solved your homework here. It's okay. And what I'm using here is something that we will discuss today. It's how I can use functions, and we'll see that in a second actually. So right now I want to look at this tree and to one more tree that Areti wrote, but not as a tree. She wrote it as a proof, and I responded with how the tree looks like for corresponding to this proof. And the tree was like this. We were trying to prove, yeah, I'll write the tree and we'll see what it proves. So it was something like y is equal to x, and this was inferred by using that x is equal to y, and what else? X is equal to x, and this was inferred by reflexivity. Okay. And this was some substitution. And the idea is that I'm using this equality to substitute in here, and I want to specify which occurrences, one or more, I'm swapping here. And actually here I want the first one, and I have not decided yet if we start counting from 0 or from 1, but let's say 0. This means that this is the 0, and this is the first occurrence of x. And here reflexivity is kind of implied that I'm asking for the reflexivity of x. I hope what I'm writing makes sense. But the point I want to make here is what's going on here. If I look at this tree, what is being proven here? And the way to see this is to look like top down and look for open branches. By open branches here, I mean things like that. This is not an open branch, it has been closed from this line. So I'm looking for open branches. And what this tree establishes is that with these assumptions, all the open things, in this case it's only one, I can conclude this, I can construct this. So in summary, I could say that pretty much this corresponds to a certain derivation for this rule. If this was, okay, let's go back in time. I'm here so far. So this makes sense. This is a valid proof, but it has an extra assumption than the original one, because now these are open branches. So if I look at this tree, what this tree establishes is this. If you have x equal y, and if you have x equal x, you can prove y is equal to x. But maybe we're not satisfied with this proof because it has more assumptions than it needs, and we say, give me a minute, I'll try to close this hypothesis, and we can do that actually by using REFL, as we saw. So the moment I do this, now my tree corresponds to a different, to a proof of a different theorem, let's say, because I have less assumptions, and this is good. So this goes away, and now I have this. Does that make sense? Okay, so any proof pretty much that we write in mathematics is a way to describe this kind of tree. And it's a quite natural way to see the structure of these proofs like trees, and we see how we can compute with these things as well. So this establishes what? This is not the substitution. Somebody spotted this, Asterios spotted this on Zulip. The question was wrong. We are establishing what? The symmetry, the symmetric rule. Okay, so this is the fact that equality is symmetric. And I will not do it here, but it's for you to prove as well that it's transitive. So the whole point is that the equation is only needs these two, let's say axioms or rules or properties, and these other two are derived if we know just substitution and reflexivity. So this is pretty much the last thing we did, and I said that eventually we have to talk about functions and notation that I'm going to need, and I have like a big complaint about the mathematical community on this, but there are some things that mathematicians are not used to seeing, and as a consequence, they're not used to using as well and to appreciating. And let me give you an example. So let's say you're in number theory and you're trying to prove to show that a certain number has a property. I don't know, maybe that it's the greatest common divisor of something. And let's say, this is a silly example, that the greatest common divisor will end up being x plus y. You have some integers, and you want to say that the greatest common divisor is x plus y. And nobody stops you from doing that. You can say, I don't know, the GCD of, I don't know, A and B is x plus y. And this makes total sense. And imagine someone trying to do the same thing and say it has a limitation, saying, no, you cannot say x plus y because it doesn't have a name. We have to give it a name. So this person would do something silly like this. Let d equals x plus y, and then they would write the GCD of AB is d. Now, if you keep using d, x plus y, maybe it makes sense to give it a name, maybe a better name than that, but in any case, maybe it makes sense to give it a name because you'll refer to it a lot of times, and maybe you want to indicate some kind of psychological value to how you see this x plus y and so forth, but you are not required to do so. It's perfectly fine to just call it by this name. Let's say, it's not a name, but describe it like that. So the sum of x and y. I don't need to give it a name. And you see this sometimes in programming as well. People do stuff like R, let's say I'm thinking of result, is equal to x plus y, and then you see something like return R. I mean, okay, why give it a name if you are only going to return it? Just skip this part and write return x plus y. So we understand, all of us, that it makes sense to describe things without necessarily giving them names. But for some reason, this tool has been taken away from mathematicians, and usually they don't have a way to describe functions. So if you don't want to produce an integer, like in this example, and you want to produce a function that does something, you are more or less by cultural unfortunate circumstances to say something like, let f of x equal, I don't know, x squared plus 1, and then say something, the function we are looking for is f. Okay? So, I mean, why? Why give it a name? Sometimes you see something very ugly. You see things like the function we are looking for is x squared plus 1. But technically this doesn't make sense because x squared plus 1 is not a function. If it is something, it is whatever the type of x is, which looks like an integer. So if this thing is a function, if this thing is something, this is an integer, but probably if we're calling it a function, it's not even an integer because probably x is not around. So like the function is this. So this has like, if I have some x lying around, it better be an integer. And if it is the case, this is not a function, this is an integer. And if I don't have an x around, this is meaningless. Because this is nothing, right? What you mean at this point is the function is this, right? And we have seen this notation. It's the function that takes an argument and squares it and then adds 1. But we have seen some limitation about this notation as well, because I might have like a lot of holes, and maybe I want to say that actually the first argument should be duplicated here, and similar stuff. So we need access to regain access to a notation that in mathematical texts you see it like this. It's the barred arrow notation, famously called maps2, which is an arrow with this bar. And it's different from the other arrow because it shows, it's like, okay, I'll draw this picture. So like I have a set or a type, I don't want to get, it doesn't matter right now, A and B, and I'm drawing this normal arrow from A to B, so I have a function, let's say, from A to B, while here I have a mapping that shows where each point gets mapped to. And I don't know, maybe I have some things like that. So these barred arrows go from points of my domain to points of my codomain, while the arrow goes from the domain to the codomain. I hope this distinction between the arrows makes sense. And we use this notation to create anonymous functions on the fly. So if I write something like that, now I can use it. Now it's legit. I can say the function is this. And how do we read this? This is the function. We read it in a kind of complicated way. I'll take this here. So this would be something like, how do I pronounce this? function that given everything I have written so far is just the pronunciation of this thing, okay? This open parenthesis, okay? So now I just copy paste the name of the argument here. I'm calling it x, sorry. Given x returns, maybe I should use a different color, I don't know, returns. And now I just translated this symbol, and now returns this thing. And how do I pronounce the last parenthesis? I don't, it's silent. Returns this, nothing, okay? So this is the notation. You will see it in certain texts, mathematical texts, usually in algebra, to refer to the actual function, because we want to differentiate also, another problem we have, we want to differentiate this thing, this guy here, from this guy here. And you'll see it, mathematicians abuse this thing all the times and say things like the function, I don't know, cosine of x is periodic, or I don't know what is your favorite property. Periodic. This doesn't make sense. I mean, we understand what we mean, but we don't mean that. We mean the function cos. Cosine is a function. The cosine of x, supposing it is something, it is like, I don't know, a real number maybe, or a complex number. I don't know how you type the function cos, but let's be honest. This thing is not the function the person is talking about. They are talking about this thing here. Yes, Manolis.
And that's the same problem as before when you said let f of x equals x squared plus 1. Like I say that all the time, books and stuff. I'm like, no, that's not a function. Like,
You mean this thing?
yeah,
No.
it's the same problem there.
No, if I write it like that, it's okay, because I'm kind of interpreting this as, okay, yeah.
Yeah, but that's for a specific integer x. Like,
Okay, yeah, there is an implicit, it's a different kind of problem here. There is an implicit convention, let's say, that we say, okay, technically what happens here is the following. We say let f, let's say, from natural numbers to the reals, or, I don't know, it was integers to integers maybe, be the function defined by f of x is equal to x squared plus 1, and there's an implicit here as well for each x. For each x, I get an equation, right? But nobody thinks about it when we do it like that. But so this is a detail of things that are implicit there, but this is not the same problem I'm specifying here. Here, it's a type error. Here, it's not a type error. Here, it's like a convention. While here, you are giving me like a real number, while and you're calling it a function. The function is cos. The moment cosinus got applied to something, the type of this was whatever the codomain of the cosinus was. Okay. So lots of sloppy things, and we get away with it because it's like we understand what we're saying. But here we will need to pay attention to these details and be honest about this. So yeah, now I have access to this, and I can do something silly. I could say something like let f. I'm defining f to be this thing. This is fine, and this is like equivalent to saying something like let f of x in the first case, there's a psychological difference between the two. In the first case, I'm saying what f is. I'm saying f is this function that when got applied to x, it returns that thing. The second one is not exactly equivalent because I'm not defining what x is, what f is. I'm defining what f of x is for each possible x. It happens that if I know this, I get to know f, so if I manage to define this green thing here, it will become green, I hope. The fact that I know f of x for each x means that I have established which is the function I'm talking about, so I get the right to say, essentially, I have defined f as well. Not directly, indirectly, I get the right to say I have defined f through an infinite and possibly infinite number of equations, because this is what determines a function. In order to get the right to say this, we don't have it yet, I have to say what equality means for functions. Essentially, two functions will be equal if we cannot observe a difference between the two. So this means that this equation, all these equations for each x, completely determine which object I'm talking about, so I get the right to say that I have defined f. But it's kind of different to use this or that. Here I'm saying f is this. Here I'm saying f of x for any x is this thing, and therefore you know what f is. Is it too philosophical, or am I okay? More or less? Okay. I see some happy faces, and I will ignore the non-happy faces. Okay, so the notation we will use will not be this, but it's completely the same idea, just we spend less ink and we pretend that we will save the planet with this, and we use the lambda notation, which is written like that. Instead of writing this, instead of writing this, I will use lambda. The same thing here, x. These returns will become a dot, and then the same thing here. So this is exactly that. The function that given x returns x squared plus 1. And some nice thing now is that I can write quite conveniently functions that return functions. And let's see this. I can write something like that. Lambda x, lambda y, x squared plus y. So how do I visualize this? Let's read this together like it's the function that taken x returns what? There is a missing parenthesis here, which will be implicit from the convention I will tell you right now, that when you see a dot, you go as much as you can without breaking any parentheses. So the way I wrote it initially, without parentheses, I would expand until the very end. So there are implicit parentheses here. So this is the function that when taken x returns a function. Which function? I'm telling you right now, right here, which function it is. It is the function that when taken an argument y, it returns x squared plus y. Which is this x? It refers to this x here. Which is this y? It refers to this y here. It gets very ugly if you don't have access to this thing. If you're programming, let's say, in Python, you are forced to give names pretty much. I mean, technically Python has lambdas, but let's pretend we don't know that. So if you've taken a course in Python first programming here, probably you haven't seen lambdas, and you would do something like that. Def, I don't know, an f of x. And then you want to return a function, so you have to create this function, and it becomes very ugly. First of all, because you have to name it. And let's say you named it g, and now this is g of y. And then you say something like return, I don't know, x squared plus y. And now, this thing here, this little definition here, has created this function that you want to return, so you still need to return it, and it's kind of the ugliest thing you can write. And I hope you agree that this kind of notation makes things way more easy, because you don't have the obligation to give names to things that you want to use when these things are functions. This notation will, I hope we will get used to it by using it. I just needed to state this, like, for people who have not seen it, and I think we have people who have not seen it. So I hope I can start using this notation from now on. Any questions about this? Yes, Aradi? If I didn't have any convention, I would be forced to tell you where are the things, what is the scope of this lambda x, and I would be forced to use these parentheses. But thanks to the convention, these parentheses are all implicit. the convention is that from any dot of the lambda notation, go as far as you can without breaking any parentheses or something like that. Maybe we'll find out that I need to specify something extra. I think it works, what I just said. Are we fine? Okay, so now that I have this, I want to come back to a question that has not, I think it's in the first set of homework questions. What are the types of these guys? So far, we have seen types, let's say, like this, alpha, or alpha cross beta, and more complicated things like that. Maybe alpha cross beta to, I don't know, alpha to gamma, I don't know. We have seen things like that. And the question is, like, first of all, how many types have we seen so far? And if we only have these guys, the answer is 0, because these guys tell you how to get a new type out of existing types, but if we don't have some primitive types to begin with, or if we don't define some types, some actual types, we don't get to say that we have any type at all. I have been using some types as toy examples, like the integers or persons or countries, I don't know, or mammals or things that can be born and stuff like that. But these are like examples that we have not defined these types. If I have these types, actually, I only need one type. Let's say I have the integers. Somebody gave me the integers, and now I ask again, how many types do I have? Any answers? Manolis? Yes, I have an infinite number of types. Give me like 2 examples that make it obvious that you can generate an infinite number of types. Yes?
Functions from integers to integers.
Okay, that's one type. Give me one more.
Functions from that to itself.
Okay, you're growing too much. Okay, I would say, okay, let's say this. Okay, and then this, all these guys are types, different types, and suddenly I have an infinite number of types, and that's fine. But I'm just emphasizing that these, so far, let's say I don't have any types at all. But coming back to my question, what should the types of these guys be? Ideas? No, yes, Lazarus.
Given 2 types, we get a new type.
Okay, Lazarus is very careful and phrased it very nicely, so I will again pretend that he said something kind of different. Let's pretend that Lazarus said that, okay, this thing gets 2 types and it returns a type. Because it looks like I'm using it like that, right? Like when I write int to int, this thing is a type, this thing is a type, so what did this guy receive? A couple of types, and what did it become? The whole thing is a type. So it looks like it's getting a pair of types, and it's returning a type. But there is a kind something like not very comfortable here, because I'm saying what the type of this thing is, and it looks like I'm using it in its own type. So the way we'll get around this thing is kind of similar, since I do have mathematicians here, and probably they will appreciate this thing. A lot of times in mathematics, you are studying something that has operations within it, let's say a vector space or a group or a ring, I don't know, and you call them operations, usually, right? And then, when you become a bit more like advanced in the next chapter on the book that you're studying, you find out that besides those guys that were like your ring operations or your vector space operation or whatever, there are some operations on a different level that take a vector space and another vector space and produce a new vector space, or take 2 groups and produce a new group. You have like the product of 2 groups. Let's say this G is a group and this H is a group. You get to study the Cartesian product of 2 groups. Or you have some topological space and you say, aha, if I have 2 topological spaces, I can create the product of the topological space. The topological space is not a very good example because you don't have an operation within it normally. You just have like open sets. But the group and the ring is a good example because you have operations inside your things, and then you have like big operations that handle those things. And usually they are called something different, like constructions. Let's see a binary construction on the groups. You take two groups and you form a new group out of that. So it's the same thing. We will consider these things to be like constructions in types, and the notation we'll use, we have already met it, so don't worry, no new notation. We'll say that if I have alpha is a type, and if beta is a type, then I can infer, I hope you're getting to appreciate this notation, that alpha rho beta is a type. This is like the type theories, or the maybe categorist way to say that I have a construction, a binary construction on types. And I don't have the problem I used to have. And it's exactly the same thing with cross. So this was like a tricky question to get you to think of the problem you have if you just blindly say, it takes two types, so type cross type, and it produces a type. So we need a notation to indicate that this happens on let's say, on a higher level. So far we have these types. Is this acceptable or? Yes, Malolis.
I'm not sure I understand exactly what this inference is supposed to be. Maybe is it like an axiom, a law, a rule?
It's called an inference rule, and with a bunch of them, we get to set to build the system we are using. So far, we haven't really done anything. Okay, I'm still a bit informal, but maybe today or maybe in the next lecture, I don't know, we'll get to actually start defining the types, and we will have for each, let's call them constructors. They're constructing types. I will have to say how they construct types. So I've done this here, okay? And then I have to tell you like how these types behave and how their elements behave and how we compute with these types. And if I do all these things, I'm done defining a certain type. We will see an example. I think it will start making more sense. And we are using this notation for, and abusing this notation as well, for a lot of things because it's extremely convenient. And it helps us separate those things. And you can think of, this is not exactly correct, but I don't know if you also have some doubts about, or some questions about how we use this symbol. It's kind of similar. It's like a one-line version of this, but it's not the same.
No, I don't have a problem with the notation in general. I'm fine with the notation. I have a problem with philosophical doubt about whether it's reasonable to use it in this specific case, because we're saying that if alpha is a type and beta is a type, and that thing down there is a type, but that thing doesn't already make sense to say that this thing exists and now it's a type.
This is part, like one of the many things that I have to do in order to get the right to tell you, now you know what the arrow is. Because so far, I'm just saying that given two types, if you put alpha, arrow, beta, it's a new type. Maybe alpha, arrow, beta, for any alpha and any beta, is the type of integers. This is a valid possibility with the things I have written so far.
So it's incomplete.
It's like when you start studying the theory of integers. So first of all, you should see like the types of those things, and here you have something like this: int cross int to int. So you know that the sum, if you have two integers, you can combine them with this weird cross-looking operation, and you will get a new integer, but you have no idea how this works. And then you study the axioms of the integers, and for example, you see an axiom that says something like x plus y is equal to y plus x. So at least you know that if you combine them this way or that way, it doesn't make a difference. And then you have further axioms and you become to understand better how these things work. But for the time being, with the thing I wrote down, maybe any type you give me here, like person to, I don't know, country, maybe this type is the type of integers. I hope it will not end up being, because it will be kind of ridiculous. But if the only information here is you have a binary construction types, that's it. And the same here. So I need, for each of them, I need to do more things to get to say, I know what the arrow is. Okay. I think now is a good opportunity to say what these things are that I need to do and have a bit of discussion about it. So first of all, I need to tell you the formation rules which is exactly the thing I did here. So this would be called, this is the arrow formation rule, tells you how you can form this type. And this is what it says. If you have any type alpha and any type beta, you can put them together and form a new type, which I will denote like that. Okay? I could denote this like any weird way you like, but it's very standard to use this notation, so I will use this notation. The idea, this symbol does not exist before this moment. The idea is this is part of the definition of this symbol. So the formation rules tell you how you can create this type. Now, what I also want to know is how I can create elements of this type and what use they are of me, how I can use elements of this type. And then, I'm still not done, because I don't know how to compute with these elements, so I need further to establish some equations. This is exactly the thing that you do in group theory again. This is like algebra, I don't know, 2.0 or something like that. Because in algebra, you state the things you have in a group, and you're not done. You have to say what equations are valid in a group. Algebra is operations plus equations. And the equations determine how these things compute and how these things work out. And so we will have to do this for types as well. So maybe my first example here should be the product. I will start from this thing. So let's see. I have the formation. I have the formation rule for the product. And let's talk about what else might I need here. This is the formation of this guy. Okay, so I need to say how I can create objects of this type, and I need to say how I can use objects of this type. And now comes a really important question, sometimes. Which do I do first? Because usually we want these are called the introduction and elimination rules, and usually we want these things to have some kind of coherence between them. So like, I'll give you an example right here. Let's say I want to see how I can create things first. Okay. So here comes the way to create elements of this type, and I say in order to create an element of this type, I need an element of type alpha and an element of type beta, and if I have these two, I should be able to create an element of type, the desired type. Here is alpha cross beta. Okay, so let's call this thing B, and now I need to come up with a notation. I could use something like pair, because I like this word, pair of AB, maybe. But it's very standard to just use this notation, and I will use it, which has a comma, and sometimes brackets as well or not, but it looks like the comma is the principal constructor here. And I need some way to write my arguments here. So this is like the introduction rule, and I'm telling you how to create elements of this type. So you have, I know it's a type, this thing, because of this rule, and I'm saying in order to create elements, you need some element of the first type and some element of the second type, and this gets you a way to put them together and create an element of this type. There might be other ways to create elements of this type. They happen not to be for this case, so I only have one way to construct elements of this type. And this is called like the introduction rule for the product. I still haven't told you how to use these, so let's do this now, which is, given an element of this type, I will call it W, because it reminds me, the letter, that it has like two things in it, but it's just something. I have a name that's an element of this type. How can I use it? And now, the idea is I don't want to start doing random things and say, let's study this system because I like these rules. It makes sense to look at what happened here. And the idea is that information went inside the construction of this guy. And I'd better be able to extract this information. And there are like two pieces of information that got inside here. So I'm expecting two ways to use this thing. One way that would extract this information, and one way that would extract this information. So I need just to find notation for this thing, and I will, unfortunately for you, use many notations for the same thing, depending on what feels more readable. So I need something. First of all, what is the type of the thing, and then let's see what kind of notation we can use. I need to be able to extract something of type alpha. And similarly, I should be able, out of this, to extract something of type beta. I hope this makes sense. Right? Okay. So I need notation. And the notation I will use should involve W in some way because I'm using it. And okay, let's write a bunch of notations. One of the standard notations would be out L. This out indicates that I'm taking something out of this thing. And this L is like left. So in this case, I will use out left, out right. Different notations I will use would be like the projections. Sometimes are called P0 and P1. Or maybe the whole word. Okay, I need more space. Maybe the whole word here. Like P0, P1, maybe, I don't know, proj maybe left. There's literally an infinite number of things I can do here. Another notation that I will use is like some kind of dot notation that is quite convenient. I'm taking the left part of W and I will write it like that. And for those who have seen something Haskell, it's a very good, yes, very common as well. So let's call it like first, like Haskell does, first and second. And I think we'll have enough for the time being. Probably we'll use more. But okay, these are just the names. So these are elimination rules. In our vocabulary, I would say usage rules. It tells me how I can use this thing. So this thing is like, and I have two, so I'll call them like 1 and 2, or maybe left and right, I don't know. And I was expecting to see 2 exactly for the reason that there are 2 pieces of information that came here. So you don't get to make some exactly arbitrary things and say, let's study this. There has to be some coherence. And so far, we haven't used equations to establish reasonable things. This coherence will come right now because, for example, I want, if I have 2 things and put them together by using this thing and then take them apart, I should be able to get exactly the same information that got in and not arbitrary things. And some like this, and the other way around. Like I'm trying to say that introduction should be like a post-inverse to elimination, and elimination something like a post-inverse to introduction. And it's a time for a break, so let's have a break now. Okay, so we have done a lot, but still we don't have the right to say that we have defined that I know what the product means, because I don't know how the elements, how I can compute with this thing, essentially. So I need equations. It's like I'm doing group theory and I only stated the operations that I have in a group, and I haven't written down any equations. So it's kind of similar reason why I don't get to say that I know what a group is. Okay, suggestions. What kind of equations should I write down? I also have the notation, and I don't see it. Okay, we were, sorry for this. I will bring this here. I want everything on the same page. Okay, so yeah, ideas for equations. Yes, Lazarus? This should be implicit, yes? Okay, perfect. So let's write down the first one. You like first. So the idea is to emphasize this idea of post-inverse that I mentioned. If I have A and B, and I put them together in a pair, and then I extract the left part, this should be equal to something. And Lazarus suggests it should be equal to A. I hope we are okay with this. And in a similar nature, there is a second equation, very similar to this one, that is like how the other, sometimes they are called like distractors or deconstructors or extractors of information. So how the other one behaves, and this should be a B. Are we okay with these equations? Okay, I need one more, and I need to discuss a bit the difference in nature between these equations that Lazarus said and the rest. Manolis.
W equals L angle outer W, comma outer W.
Equals, say it again, sorry.
L angle, symbol.
Yeah.
Outer W.
Great.
Comma outer W.
So, these equations are fundamentals. I remember the first time I read this on a text, like these are very fundamental things, I said to myself, come on, this is ridiculous. Nobody would ever think this as very important, that W is equal to like extract the left part from W, extract the right part of W, and then put them back together and you get back W. This seems kind of silly. But you'd be surprised of how fundamental indeed it is. These, I will start using names here, tell you how to simplify things, while these things seems like it's kind of complicating our life, if I read them like left to right, and we tend to read these things like from left to right. These kind of more deserve of the name computation rules. Reduction, maybe. Something gets reduced, maybe, okay. But the real name we are going to use for these things is a Greek letter for some reason. Church used this. It's called Vita. While these guys here, which we only have one, is called Eta. And the only way to appreciate that, start feeling that this is a Vita thing and this is an Eta thing is by seeing it again and again, and then we start to realize that they are things of a quite different nature. In a certain sense, maybe someone would say that this has the flavor of something we should be able to prove, while this maybe has the flavor of something we demand. We'll come back to this, it's not for today. And this is also corresponds to a certain uniqueness. And usually I attribute a homework exercise here to kind of understand why. Because I think that if I call this uniqueness property, it seems like I'm just using a fancy word for something that doesn't really look like unique. There are two ways to see why you could call this uniqueness, but for the time being, I will call it Eta without saying why, and there's no why actually for Eta. It was just the letters that church used for some similar rules. But pretty much every type we will say will have some Vita aspect, which tells you how to compute with these things, and some Eta aspect, which tells you that you can, there's some kind of uniqueness involved with these constructions that you have. Yes, there's yes, it's exactly the same thing. This is so for whoever has seen lambda calculus, you have Vita reduction, which is the vita rules for the arrow, for the function. And the eta, convergence or equivalence, maybe it's called some different name and not reduction, because it usually expands. Eta expansion, maybe, I don't know. But the eta in lambda calculus would be the eta rules for the arrow, for the functions. And so this is for the more computer scientists here. For the mathematicians here, we have exactly the same thing. I mean, for sets, set notation does not suffer so much as a functional notation from mathematicians, because you have the way to specify sets without names. Okay, I will open this parenthesis. It's a good opportunity. So every mathematician understands. Okay, supposing this is a curly bracer, like, I don't know, I have something like x is greater or equal to 5. If I write something like that, you know what set I'm talking about, even though I haven't given it a name. You will not say, how do you call the set? It's this set. And how do you pronounce this? I think I can even copy-paste this, right? It's quite similar to this pronunciation. I don't know how to copy this. Okay, I do. I'm copying pasting it, not because I don't want to write it, just to show you the similarity. So this is like the set that consists of all x's such that, okay, so it's pretty much the same thing. Okay, it's not the same thing because it's a set and not a function, but the idea of the notation is pretty much the same. And this whole blue thing is again how you pronounce just this symbol. This thing again is silent, you don't pronounce it. And this returns thing here is just this guy here. Okay, so you are used to creating on the fly nameless sets, but not functions. So what would be the eta thing for sets? Can anybody see this? So like I'm looking for the similar idea. What happened here? It's like you have a pair, you take out the left, you do what you can do with it, and then you put it back together in a pair, and essentially you want to say something like you ended up with the same thing you started with. Is it Stelios? Sorry.
The two sets are equal, are the same set if and only if they have the same elements?
What Stelios is saying, which is the extensionality of sets, is extremely very related to the thing, to eta, but technically I want to see it as an equation or as an equivalence. It's the principle behind this is this, and if you have this, you can pretty much prove this eta thing. Manoj, what's your suggestion?
A equals x such that x is in A.
Exactly. So it's like if you have an A, and you take all the x's of this A and put them in a set, this should be the same set that you started with. So like x in A, this presupposes that I have an A in the same sense that this presupposes that I have an element of this pair, right? So if you have an A and you take all the elements of A and then say, give me the set of all x's such as this thing should be equal to A. This should make sense to everyone, I hope. And this is exactly the eta equation for sets of some type. There is invisible type things here, okay, because our sets are well typed. I will not write this. It's like, okay, but I hope and this technically this equation is among sets of type alpha. But all these things are like implicit and inferable. And what would be like the Vita thing? How do you compute with sets? The equivalent thing would be like if you have something like that a certain A is inside this set, let's say I have this in my givens. I know that the A is the element of the set of all x's such that phi of x. What can I get from that? phi of A, right? This is the Vita aspect of this thing. And we'll see again, every type pretty much will have a Vita and an Eta aspect. The Vita will tell you how to compute, how to simplify things, how to use these things, and the Eta will tell you, will give you some kind of uniqueness property. If you get a set, and you pretty much put all of its elements in a set, you didn't lose any information. So the set was not allowed to carry extra weird properties or hidden stuff that you cannot access by this interface, like tell me if something belongs here or not. Yeah, questions so far? Okay, back to functional notation, because there is one more thing that maybe mathematicians are not used to it, and I need to establish this. So usually in mathematics, we have this notation. We write, if we have f that goes from alpha to beta, and if we have a of type alpha. Okay, I'm doing two things at once here. I'm giving you the introduction rule of the arrow, and at the same time, I'm discussing how to. Okay, what should I be able to construct with this thing? I have a function from alpha to beta, and I have an element of alpha, so this should be enough for me to construct an element of type beta. So I just want to know what the notation is. I could use something like the application of f on A, or I could use something like the evaluation of f on A, I don't know. But what we will use, indeed, will be the most economical of all, which will be just f, a little space here, and A. And this will be our notation for function application. I don't want to use this. We will, you can use it, but it will become very cumbersome to write all of those parentheses. So here there is an invisible space operator, let's say, some syntax that denotes the application of something, of a function from alpha to beta, to something of the correct type. And so I have this typing rule. Is this okay? For everyone? Okay. So just a small, like trying to defend why this is convenient. This kind of shines if you have carried functions, like if you have something of this type. We know that this is isomorphic, even though we don't know what isomorphic means, but we know it's isomorphic to this thing. It's not the same, it's just isomorphic, which means that if somebody has like, let's call it big F, and this, let's call it small f, whatever you can do with the big F, I can do with small f, and vice versa, almost. But how would I call the small f? I will need to give it an element of its type. And maybe you are used to thinking of this notation as some kind of special function application notation. If you are doing math or if you're programming in C or Python, you are pretty much, your eyes tell you that something like this, I don't know, A, B, C, that this parenthesis and this commas is a special syntax that means this. Apply the function on the left of this parenthesis to this, and here are your inputs, okay? So we are pretty much programmed to think like that. I don't want to write it like this. For binary things, it should be like that only. No special parenthesis function calling syntax. I will write this like that. F, and then this little space that I will not write, but I will leave a little space there. And here is like the only argument that f will take, which is a, comma, b. Does it have the correct type? It does, because my little f wants something of pairs, and this is a pair of alpha cross beta. So there's no special notation here. This thing is just the constructor of the pair, and the actual function application is this little invisible space that I have here. And my friend who is using the carried version would do this like that. Would write something like f. Now, what is the domain of f it's alphas. It's alpha. So I need to give it an A. So let's give it an A. And now the question is, what is the type of this thing? And to answer this, I need to know the type of F and see how I can infer this type here. So F gets an alpha, which it got, and it becomes this thing. So the type of this thing is from beta to gamma. And this means that I can apply this thing, since it's a function from beta to gamma, I can apply f of a to something of type beta, and this will be gamma. If someone is lost, let me know. So this notation, I hope it makes sense. It says like you have this f here, give it an a, so now this whole thing became a function from beta to gamma, and so give it a little b, so now this function is just type gamma. And we'd better have some syntactic accordances here, so that I don't need to put parentheses when it's convenient not to. Okay, so any questions so far? Okay, so the syntactic things I want to discuss, and I want to give them a name. Oops, I thought I have this. Okay, it's here. Syntactic aspects. I will come back to the number theory. I'm trying not to give too many weird examples for mathematicians who have not programmed much. So like, let's say you're doing the theory, you're studying the theory of integers, and together with the integers you have a bunch of things, usually. Like you have times, you have a 0, and you have a 1, and maybe some other things, I don't know. And you have the types of those things, as I said earlier. So for example, this thing goes from int to int. And similarly for the multiplication, this minus sign that I have written here is actually unary. So maybe I should write this down. But it's not so important at this moment. And you have the types of the other two guys as well. What are the types of these? Somebody please help me. Yes? Int, just integers, okay. So these are all the operations you have on the integers. And eventually you want to write something like that. And then you have some axioms. Like, for example, you have the axiom, this is my main point here, that plus is associative. And then eventually you see something like this. A plus B plus C. And the question is what this thing means. Yes? Thank you. This is this thing? Thank you. This is a multiplication. Okay, so you see something like that. And usually you say, I know what that is. It's the sum of A, B, and C. But no, you're cheating because this is meaningless. Because if you see the type of plus, it's just binary, and it looks like you're using it on like 3 arguments at the same time. And it would be a mistake here to say, but it's associative. Okay? Because being associative tells you, what does this property mean? It means that A plus B plus C is equal to A plus B plus C. And this is a property. This is a mathematical property which, given a certain operation, you can prove it or disprove it, you can investigate it, you can ask, is it associative or is it not associative? And this is called associativity. And you all know it, I suppose, as a mathematical property of an operation. It doesn't make sense to say, I will decide that this operation is associative. You don't get to decide. If you already have the operation, it either is associative or it's not. You don't get to decide. It's not a matter of let's agree to call it associative. You cannot take, for example, I don't know, let's think of a non-associative, like exponentiation. It's not associative. You don't get to say, I will decide that it's associative. You get to say, I will decide I will denote it like that. Okay, so again, the difference is between the world that this operates and this operates. So this associativity is a semantic property, mathematical property. On the other hand, this thing has absolutely no meaning, and we have to decide what kind of meaning we'll attribute to it, and we want to say, for example, that it means this thing. And this thing is called syntactic associativity. And this is completely syntactic, okay? And this we get to decide. Because this means, let's agree that whenever I write something like that, what this denotes is this. And now we have to, this happens for for operators used in infix notation, like this. This is the infix notation, which means I put an argument, and on the two sides I have like integers in this case. So if I don't do this, and I write this, it means nothing. The compiler will say, I don't know what you're talking about. So if I establish this, anytime I write an expression like that, it means it's just sugar, just an abbreviation of this thing. And it would look very ugly, but in theory, I could, if I have this, I could express this property like that, and most proof assistants will do this. Will say, humans like to see, since they established the syntactic sugar for associativity, the syntactic associativity, they prefer to see less parentheses, so let's write it like that. And I would argue that this is like one of the few cases that you want to see the parentheses there. You don't want to remember where, what the convention was, and it's not very indicative to say it like that, so it's better to actually write the parentheses here instead of trying to remember what's going on. And we'll see that there are commands that they make the proof assistants show these implicit parentheses, because a lot of times you would say something like, you will have this, and you will know, for example, that b plus c is equal to 5, and you will want to rewrite this and say, substitute b plus c with 5, and the system will tell you there's no b plus c here. Because you are seeing it, but actually there are some invisible parentheses here, so use associativity first, so that the parentheses changed place, and then replace this by its equal. Are we okay with this idea of syntactic associativity? Okay, so which syntactic associativity would we attribute to the plus sign here? And be careful, I'm saying to the plus, right? It's not to the addition. It's not a property of addition, it's a syntactic property, that's why I'm saying to the plus. And you can say that, okay, it's the integers, the operation will end up being associative, so I don't care. Pick one. It's fine, it's a good answer, pick one. We don't care. But when you reach like an operation that is not associative, like exponentiation, it might make sense to pick one or the other. I don't know if you want to denote like that or like that. And now let's say, okay, for exponentiation you can say like the whole humanity knows if this means this or that. And we don't get to change this, but let's pretend that this has not been decided yet. And we are in the table that we're going to set for humanity. Should this thing mean this or that? There's a good reason to choose one or the other, and surprisingly, the convention is a good one. I mean, okay, which is the convention? This is just, I'm getting to see if you know what this thing means. Usual mathematics, yes, Marolis? The second one, yes, this one. Okay, and you can say it means this because I learned this in elementary school, so let's not change it. That's a good reason, more or less. But I'm trying to argue that if we had to decide one of the two, it would be more convenient to mean this. Anybody has an argument for that? Yes, Lazarus?
What is more common, right?
It's more, I don't know. Okay, first of all, if it is more common, I'm not sure, but if this appears way more, you'd say, okay, I'd rather to save ink on parentheses and write it like that. I wouldn't think so. Maybe, let's say it's 50-50. Okay, we still have a good reason to choose this over that. Any idea? Manolis?
The other one can be simplified like straightforwardly.
Yeah, okay, so the first one happens to be equal to this thing. Right? We know this, we learned it in, this was elementary school, I hope, right? It was not high school. No? It's high school. Okay, so we learned that in high school. So if you want to say this thing, like you already have a way to say it without parentheses, just write it like that. Okay? If you want to say that thing, you are gaining now a way to say it without parentheses. So it's not so trivial. It's not a mathematical thing, but it makes sense to worry about it when your operation is not associative. Okay, so this is all I have to say for the time being about syntactic associativity. Another syntactic aspect, so associativity is when the same symbol, like plus, these two plus signs are like arguing which will get to use the middle term, right? This is resolved by syntactic associativity. The other thing is syntactic precedence, when you have more than one binary symbols, for example, this thing. So if I write this, this is meaningless until I get to say that this symbol plus over the dot has a higher or lower precedence. So this would be the syntactic precedence. This resolves situations like this when you have two different operators like fighting for the guy in the middle, okay? So associativity, so syntactic associativity resolves when two pluses fight for the middle guy, and syntactic precedence is like, if I know that this thing has a higher precedence, it will be interpreted like that, or the other way around. And for example, in the integers, we have that the multiplication is higher precedence, so if I write this, it means this. One final, I think, convention is like if you have a default binary operation that you just denote by juxtaposition. And this, for the example, in the integers, we say that, okay, if I write something like this, A, B, C, D plus E, juxtaposition, the default operation will be multiplication, so I know, using all those things in my example, I know how to interpret this. This will be something like, I will not write it down, A times parentheses B times blah, 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 blah. Okay, so there are three syntactic things that we want to establish, and my main point here is that these are exactly syntactic things that we need to settle, and if we don't, things are meaningless. Questions? Okay. Good. Okay, so we have this notation, and I want to settle some things now, some precedences, some syntactic stuff on the things we have seen so far. So this little operator here associates to the left, which means that I can write this thing here without parentheses. Because if you see what happens here is I have these invisible operators, the same kind of operator, it's the space, and they are fighting for who will get the A in the middle, and in theory it could be like that, or like that, and I'm resolving this now. So if I write just this, this means this. And this will be very convenient because it allows me to write like a function with 5 arguments in a carried way. So I will use something like f of A, B, C, D, and in my mind I read it like that. F of A, B, C, D. Technically, it's you apply F to A, and this becomes something that's expecting a B. And then you apply B to this, and this becomes something that is expecting a C. And you apply C to this, it's expecting a D. And finally, this whole thing is of type, I don't know, epsilon maybe. Okay? Are we okay with this convention? Perfect. And this is higher than this. So finally, I can stop putting all those parentheses. I can write stuff like this now, and you know how to parse this. And can I write this? Yes? Yeah, can I write this? Yes, so I cannot, because I haven't attributed syntactic associativity of the arrow. So, for the same reason, I cannot write this as well. So let's do that. Here it doesn't make much difference. Let's use left. I need to pick one. But here it does, because as we have discussed already, this type is very different from this type. Let's describe the elements of this type. They take functions from alpha to beta and map them to elements of gamma, while these ones take elements of alpha and map them to functions that map elements of beta to elements of gamma. They're completely different things. So I definitely need to decide, I need to think here which of the two I will pick. And we'll end up picking to associate on the right, which might seem a bit weird, but the reason for this is that I can write, it matches this. And now you'll ask, how does it match this if it's on the right while this is on the left? The problem is that we're using the arguments on the right-hand side, so we have to invert this. It's the similar reason why the ball notation for composition confuses some people. So let's see, I want to be able to write this thing if I have that f is of this type, the carried version of this. And the carried version of this is this. And since I will use a lot of functions of many arguments in a carried way, I don't want to keep writing all these parentheses on my type, and I don't want to keep writing all these parentheses on function application, so the convention here will be that the arrow associates to the right. This means I can write my functions like that. I have a function that goes, and I will read it from alpha to beta to gamma to delta, and in my heart, I understand this. It takes an alpha and then a beta and then a gamma to finally produce a delta. And I will call this like this, F, A, B, C. Okay, invisible things here. We can see them now. Invisible things here. And also here. A lot of invisible stuff. I don't want to write them, so I will leave this without any of these. Yes, questions? No questions. Okay. I think we have what we need. We have for functions. Okay. To start seeing, let's try to define a type. And I hope I will not bore those people who have used Haskell to death or have seen some inductive types. But let's try to define a new type. And I could define a silly type or a simple type, not silly, a simple type or a very complicated type. And I want to start from a middle ground. And I want to discuss some ways in which I can introduce the type of the natural numbers. So let's say I want to introduce this type, or maybe not. Let's call it not for the time being. Okay, so again, I have to tell you how to form this type, and the idea is that you don't need some existing types in order to form not. Not is a type. Okay, so the idea is I'm already telling you that this thing is a type. This would be if I want to write it as a formation rule, I will not do this so carefully right now, but this could be like the formation for not. Let's be a bit more friendly or more informal at this point. I'm telling you that not is a type, and I want to tell you what are the elements of this type. First, I will use the more human or common way for mathematics to specify clauses that determine what things are of this type. So maybe I would say something like, this thing is a nut. And then, maybe I have a second, pretty much, and I see this thing, I'm not calling it zero yet, because it's I don't want to give it a name yet, but it will end up denoting the idea of 0. So this round yellow thing is a nut, and then I would say something like if n is a nut, then the successor of it, and again, let's not call it successor. If you add this weird line in the front of it, is also a nut. The way I'm writing this down is called like I'm giving an inductive definition. I'm giving clauses of all possible ways that you can get a nut, and I think that people have seen similar things. I'm defining the set of natural number, I'm defining certain things. First of all, this thing is a nut, and then I'm saying how I can get more nuts out of maybe nuts or other things. Things to discuss here. First of all, what will end up being the type of 0 of this thing? Somebody help me here. Nut, okay. What is the... I painted this blue and this yellow to make this distinction clear. This n is a meta variable. I'm using it like to communicate an idea with you. This is part of English here, or of Greek, or whatever. I'm trying to say that if you have a nut, then if you put this symbol in front of this thing that you have, then this guy is a nut. So this is like a meta variable. I will, I don't know how to say this. Okay. Repeat this just to emphasize this. It belongs to English in this case. Let's say it's English. And there's implicit thing here, right? For each n, something like this. For any possible n, so this is my second clause here. So if I only see these clauses, I can already have some elements of type nut. Can I have some examples? Someone, please. Someone else? No, nobody wants to give example of a single nut, please. Yes, Aditi, thank you. You mean 1? Where is 1? There is no 1 here. You can express the idea of 1. Okay, so let's say that in our heart we have this set in the clouds of our heart, and you know that here you have the idea of natural numbers 0, 1, 2, 3, blah, blah, blah. And here I'm defining a different thing called nut, just to make it sure that it's... The idea is that my thing, if I define properly, can represent these ideas that you have in your heart of the natural numbers. And probably, so here you have like a 0, a 1, and 2. I'm not talking about the symbols, okay? I'm talking about I don't know, have a 0, and then a 1, and then you have the idea of 2 and the idea of 3, okay, so on and so forth. So forget this thing. Let's look at this thing, and I'm asking if we can produce certain elements of this type. So if you say 1, I could ask you, what is this mysterious 1 that you're talking about? Yes, Maya?
Yes, with them.
Okay, yes, S of the round symbol, right? So first of all, it's this guy, okay? This is a nut. Here's an element of this type. And then Maya is saying that this thing will end up being a nut as well. And it needs some defense. I mean, we need to defend this. It's not so immediate. So why is this a nut? And then how would you argue? Why is it a nut? The only clauses you have here is that the first and the second clause here. So in order for this to be a nut, maybe it's because of this, but this just says that this guy is a nut. Now the second rule says that if you have a nut and you put an S in front of it, you get a nut. So probably this was constructed by the second clause. But I also need the first clause because I will ask, okay, for which nut, for which n are you using the second clause? And you are using it for 0, okay? So there is a small derivation tree here. And now I can ask something silly like, is Maya a nut? Yes or no? Are you a nut? So the answer is I don't know. I cannot defend that it is because these things will only help me construct these nuts, and you can get it like that. I hope you agree that with these rules, all these guys are, and this here, I need parentheses, okay? So I have all these elements here of the type nut, and if you pick any of them, I can defend the fact that it's a nut. Okay, it will take me some time if you pick a very big one, but I will make it. But I cannot defend that Maya or Lazarus or Thanos is not a nut. But the way we read these things, the inductive definition, is that as if they have always an implicit and very important third rule, last rule actually, which says nothing else. This is completely crucial. And now I can defend that we are not, me, Lazarus, whatever, we are not nut. And this will never write down. It's always implicit. So nut is something that can be constructed by these things, and not only the things that can be constructed by these things. Hold your question a bit because I'm running out of time and I want to say exactly the same thing in maybe 2 or 3 different ways. So here, it's like the human way to define this. A different way would be to list the rules of forming nuts. And I will do this now. I will keep translating these two things in different notations, okay? So using inference rules, which will be one of our favorite way to write this, I hope, is like out of nowhere, I can infer that this thing is of type nut. And the second one is if you give me an n, if n has a type nut, then I can infer, I can construct this guy, and this guy will be of type nut. And I will give name to these rules. Let's call this, I don't know, maybe 0. And let's call this suck for successor. And there are no other ways to construct. So I only have 2 rules to construct nuts. Is that okay? Do we agree that this thing is pretty much the same thing as that thing written in a different way? I hope we do. And a different way to do that would be to just list the constructors, as we call them, and their types. So I will say I'm creating nut here, which is a type, let's say. And I will give you all the constructors, and it only has 2 constructors. It has this guy and this guy. And I have to tell you the types. And the types are, somebody help me. Yes, Konstantinos?
Nut, nuts, and nut.
Very nice. This is nut, and this is nut to nut. And again, it's implicit that there are no further constructors. I listed all possible constructors. And the final way will be, so if you have programmed in Agda or in Lean or things like that, you are more used to seeing this. If you have programmed in Haskell, you are more used to seeing not listing all constructors, but listing all possible forms that the elements have. So a Haskell programmer would like to see something like this. That nut is either this symbol, yellow, this symbol, or we are using this notation here that means something like or, this symbol apply to a nut. Depending on what you're doing, any of these can be equally informative and easy to read and all those things. So this way is telling me nuts have, each nut has one of these forms. Either it's just this, or this thing applied to some nut. This thing tells me there are 2 ways to construct nuts, and here they are. And this tells me the constructors of nuts are these 2, and here are the types. Any of these, 1, 2, 3, or 4, we understand it as defining and establishing the same thing for our system, we get to have the natural numbers. Any questions? No. Okay. So as a last thing, because we're running out of time, I want to do something with these natural numbers that I have, because I have a way to construct natural numbers. I don't know what I can do with them. And probably here, one of the first things you do is define some functions. And maybe I could define, I don't know, maybe the factorial. So I would say that the factorial is a function from nut to nut. And I would define things like this. The factorial of 0 is something, and the factorial of the successor of 0, of some n is something. And the question we should answer is what gives me the right to define things like that. But it should make some sense, because essentially I have told you what the factorial of a natural number is for all possible cases. It's only these two cases, so I have taken into account this when I'm defining this, and this is what is called the recursive definition. Because in this thing, in here, I am allowed to use the factorial. I'm allowed to use this. And this is like a big discussion. We will have to see why I'm allowed to do that and if it makes sense on all this, but you are used to that. Usually you write something like the factorial of 0 is 1, and the factorial of, I don't know, n plus 1 is like n plus 1 times the factorial of n, something like that. You are using here the factorial of n, and it's maybe kind of cyclic reasoning or whatever. It's not, because you are not. It would be a problem if you had here, if I say that a equals blah, 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 and I use a, I have a problem. I cannot define it like that because it's circular. Nobody will understand anything. But here, I'm defining n plus 1, and here, the factorial of n plus 1, and here, this thing does not show up. A different thing shows up, and it computes, as you know. We're out of time, so I will wrap things here. We get any questions or things on Zulip, and so at least we have like a type that we can start playing around with. So till next time, or till Zulip.